Welcome to the course of Advanced Classical Mechanics. My name is Mikhail Frolov, and today we're going to talk about Lagrange equation of second type. So, in order to describe Lagrange equation of second type, I have to introduce two principles or two postulates which we use in classical mechanics. So, the first postulate is a postulate about existing of Lagrange function, and that Lagrange function completely describes the dynamics of our mechanical system. So that function is a function of generalized coordinates. So L is a function of set our generalized coordinates Q1 up to Qs. Qs is a degrees of freedom of our system. And that Lagrange function also depends on the generalized velocities, which is a Q dot 1 up to Q dot S. That function may be stationary, may be non-stationary. So if that function is not stationary, that we have an explicit dependence on time. And the second principle is a principle, or postulate, is a principle of the least action. So how we can introduce that principle? For that, we have to introduce classical action, and classical action is a temporal integral from Lagrange function. So don't forget that Q is a function of time, velocity is also a function of time, so our integrand here is a function of time. So we just take an integral from t1 to t2. That is a classical action. So now we consider just simple example. Let's say we're living in some simple world where there are only three ways to connect Q1 to Q2, and Q1 is a position of our mechanical system at the moment T1, and Q2 is a position of our mechanical system at time T2. So let's say we have three ways here, or three trajectories, and along of that three trajectories we can calculate three actions, three classical actions, which we call S1, S2, and S3. So now the question. So we have a mechanical system, and there are three possibilities to evaluate the system in a time from point Q1 to point Q2. So which trajectory should be chosen by our mechanical system? And principle of least action tell us that system will move in such trajectory which can realize minimal classical action. So in that example, our mechanical system will choose trajectory number 3. So how we can formulate the general equations, which we call Lagrange equations, by using the principle of least action. So for that case, so we have to introduce variation principle or use variational principle to obtain that equation. So how we can obtain that equation? So let me simplify that problem for first sight, and we consider the function f of x, which has a minima at x equals x0. So at that point, first derivative of that function equals 0. So if we calculate differential of that function f at the position x near x0, so that as differential is also equal 0. So a similar thing we can realize for an action. So action in mathematical sense is a functional. So let's say, so we have a generalized coordinates Q2, Q is a function of t. We have a generalized velocity, which is a derivative of q. So now we consider the changing of our action if we change our generalized coordinate smallly. So delta q here is a variation of our generalized coordinates, and for that variation we have an initial condition. So we're starting from the point q1 at the instant t1 and finishes at time t2 having coordinates q2. So now we have to calculate the changing of our action, and if we in the extremal trajectories or true trajectories, so our changing of our action or variation of our action should be 0. So by using that principle, so we can obtain Lagrange equation. So let's say we know the Lagrange function, and using some mathematical calculation, we can arrive to that equation here, which call Lagrange equation. So what we need for Lagrange equation? So if we know Lagrange function here, so we can calculate partial derivative in q dot. So we can calculate partial derivative in q. Then we calculate total derivative from partial derivative of L in a q dot. And then we will have an equation for q. On the next lecture, we will discuss properties of Lagrange function by using properties of space and time in classical mechanics.